ठीक है? So 3 different ways in which I can write the same thing, which is your PCD to 7 segment display decoder. Are you getting this? Do you see the difference? Do you see the difference between these data flow, behavioral and structural type of modeling or description? All right? Okay?
Yes. Yes, sir.
And then if you simulate, you'll see all the things like this, the waveforms. Okay, at this point, I just want to, I hope you have already started with writing the code, writing the design and simulating it. Yes or no? You not yet started?
In practicals.
Practicals? Have you started or not? Guys? If not, I'll just share a screen and just point you towards one very interesting software called as Active HDL. You see the screen now for Active HDL?
Yes, sir.
Yes.
So I can start with a new design, create a new workspace like this. Okay, I'll call it as test. Okay. Create an empty design with design flow. Default language is VHDL. Design name gates. We'll just go for the basic gates here. So I'll just use the hardware description entry. Now here you can have 3 different types of entries: hardware description, or you can use the finite state machine, the state machine design entry, or you can use the block diagram entry as well. All right. So we are interested in this. This is very easy. I found out to be the best software for simulation. And this is compact. Xilinx is very bulky. I did not download all the 20 GBs of Xilinx software. This is very simple. If you want, I can share this link with this software with you, but it is a little bit unofficial that way. For those who are interested in just functional simulation. Okay, type the name of the source file to be generated. This is going to be your top level entity. I'll call it as my and gate. Okay, name of the entity is optional. It will derive from the entity itself. Okay, yeah, this is interesting. It creates all these port declarations automatically. So I can say here port, this is A, this is B, which is in type, and this is C, which is out type. So this is my, are you able to see the screen properly?
Yes, sir.
The file wizard and all that. You see
Yeah.
that my AND is created with 3 inputs, rather 2 inputs and 1 output.
Yes.
Okay. So once I finish with this, you'll see that it has already created these particular statements like library IEEE, use IEEE.std logic. That's all. Entity name, my AND. It has already declared. So all this is automatic. Okay. And many times it saves us the error, the problem which arises due to misplacements of semicolons and all those kind of things. But of course, for student level, you should remember these also. Okay, syntax and all those things. Okay, so here I am going to write the design. A very simple way of doing this will be, that's all. Okay, you can compile the design as you can see here. It's already compiled. Then I can initialize the simulation. So these are the inputs. Now I am supposed to push all the inputs to a waveform. So these are the waveforms. At the same time, I'm supposed to add stimulators. So I can use the clock here of 10 megahertz, for example, for A. For B, I can use a clock with, let us say, 5 megahertz. Okay, and then I can simply run this software, run this simulation, and you can see what is happening. See that? Are you able to see this?
Yes, sir.
Okay. So is it behaving like an AND gate? Is it behaving like AND gate?
Yes.
So for the very first experiment that you should perform is all the basic gates. Try the basic gates and see how you can simulate these basic gates. Okay? It's very simple that way. The thing happens, the thing will grow exponentially difficult once your design actually gets more and more involved. Okay, so first get acquainted yourself with the flow of the package of the design. All right. So how many of you have actually got experience of doing this
In, in second
in
year.
your lower classes?
Yes.
Yes, sir. Done.
You've already done this.
Yes.
Yeah.
Very good. So then, which software have you been using?
Xylem.
Xilinx. All of
Yeah.
you?
Yes.
Okay. In that case, we are also using Xilinx here. So probably Ankush Patil sir is in charge of your practical sessions, right? So he will be, yeah, he will be telling you how to use the software, and well, you already know. So what I do, why do I prefer Active HDL is because of the very easy IDE. Okay, so it's not necessary that you also follow the same IDE. Doesn't matter really. Okay, but then it is having a lot of interesting things like language assistant, and then you can have simple code snippets also. Okay, so you have a lot of interesting things over here in active HDL. That is the reason why I like it so much. Anyways, so okay, that's all for the demo. I'll just switch back to our presentation. Okay, so I've been using active HDL only, and you can see that the output that you get is something like this, for specifically for this BCD27. So it's one and the same. All right. So now we are going to we are in a position to see the other language elements, that is the sequential statements. Okay. So just hold on for some time before I fire up. Okay. Do you see the slide now for sequential statements?
Yes, sir.
Okay. So in VHDL, code is inherently concurrent, remember that. But sections of the code that are executed sequentially are the process, function, and procedure. One important aspect of sequential code is that it is not limited to sequential logic. There is a common misunderstanding that only sequential code will give rise to sequential kind of logic. It's not that way. Sequential logic means what? The state machines and all that. It's not necessary. We can build combinational circuits with the sequential statements also. Sequential code is also called as a behavioral code. As you can see, that it is mostly used in behavioral style of writing the architecture. This sequential statements are quite often used. So a process is a concurrent statement which describes the behavior. Sequential statements are allowed only inside the processes, functions, or procedures. This is a very important consideration. Please remember this. Okay. Very important. Sequential statements are allowed only inside the process, functions, or procedures. Sequential statements, what are they? If, wait, case, and loop. Okay. Variables are also restricted to be used in sequential code only. As I said, there are two types of, let us say, variables in general sense. One is having a global coverage, other is having a local coverage. The global coverage wala variable is called as a signal in VHDL, whereas local coverage variable is called as a variable itself. Okay, and these variables are restricted to be used in sequential code only. You cannot use a variable outside the sequential construct. Okay. Signals and variables revisited. That is the reason why we have to see it from a different angle now. So VHDL has two ways of passing non-static values. As we have said, these are nothing but they are called as variables in generic terms by means of a signal or by means of a variable. So signal and variable together can be called as equivalent of a variable in conventional programming language. Don't get confused with the name variable only and signal only. Signal can be declared in package, entity, or architecture. In its, of course, in its declarative part, while a variable can only be declared inside a piece of sequential code. This is the most important distinction. Signal is global, that is, it can be accessed from anywhere, any part of the code, whereas variable is local and can be accessed only inside that process or that piece of sequential piece of construct. Okay, the value of variable can never be passed out of the process directly. This is another important thing that you must understand. If necessary, it must be assigned to a signal and then it will be available outside the process. We'll see one example like that. Update of variable is immediate, whereas new value for signal is generated, generally only guaranteed to be available after the conclusion of the present run of the process. Because the process itself is concurrent. Whatever goes on inside is sequential. So variables are immediately updated, whereas when we talk about signals, which are actually some sort of wires or maybe uh, global variables, they are only available after the present process concludes. Okay. Assignment operator for signal is less than or equal to, while that for variable is colon and equal to. Please remember this difference. Okay, that brings us to a very important construct, and that is called as a process. So process is a sequential section of VHDL code. It is characterized by the presence of if, wait, case, or loop, and by what is called as a sensitivity list. Now this sensitivity list will not be there if you use wait. We'll see one example and then things will be more clear to you. Now process must be installed in the main code and is executed every time a signal in the sensitivity list changes. Or if you have wait, then whatever is the condition corresponding to wait, which is when it is fulfilled, the process will be executed. Okay. So as if you are having some kind of a trigger. Okay. So the sensitivity list is nothing but the trigger signals. What is this? How does the signal syntax looks like? Okay, we have the label, which is optional. Postponed again is a reserved keyword, which can be used later on. We'll see time permits. What is that? But you can just ignore it for the time being. Process followed by what is called as a sensitivity list. Then we have the variable declaration. Again, just like the signal, we have declaration modes, different types, okay, and range, etc. So you can declare it over there. Then you have a begin and you have an end, and in that begin and end, you can have a sequential code. Okay. Now, where can you put this process itself? It can put it inside the entity after begin, or architecture after begin, block after begin, and generate after begin. What are the rules? A process must contain either a sensitivity list or statements, await statements, but not both. Please remember one thing: you cannot have a sensitivity list also as the wait, also a wait statement. Every process executes once during initialization before simulation starts. Okay. So this is only the initialization part. A postponed process is not executed until the final simulation cycle of a particular simulation time, and thus it sees the stable values of the signals and the variables. Remember that a process with neither a sensitivity list nor a weight will loop forever. This is again a bad thing. Should absolutely be avoided. Now there are so many attributes that you can use. So how can you use event attribute? Okay. So to construct a synchronous circuit monitoring a signal, clock, for example, is necessary. Common way of detecting that change in the signal is by the means of what is called as a event attribute. So you have the attribute. Okay, event is an attribute. For instance, if clock is signal to be monitored, then clock tick event. So this is pronounced as tick. This is clock tick event, and it returns true when change in the clock occurs. Now, right now we don't know whether it is rising or the falling edge. As soon as the level of the clock changes, this event will return true. This was just to make you sure, make you comfortable with the example that we are going to use later on. If construct. So a sequential statement which executes one branch from a set of branches dependent on the conditions and which are tested in sequence. Again, remember it is tested in sequence. Now, whenever such kinds of things are there, like sequence and all that, immediately from the hardware point of view, you should think of, okay, can I make use of this as a priority encoding? If it is in sequence, then naturally I can make some kind of priority over here. Okay, so develop this practice of trying to correlate, visualize the hardware, even if there is software in front of you. So the syntax is, if condition is met, then whatever sequential statements, else if condition then, and else, last is else, and terminate with end if. Now this else if, you have to be careful. ELSIF. This is not a spelling mistake. This is the required syntax. If you write ELSEIF, it is going to trigger the compilation error. Okay? Is that fine? Guys?
Yes.
Yes, sir.
Okay. So you have the if construct. We'll see what is synthesizes to. So assignments within if statements generally synthesize to multiplexers. Remember that. Okay. So whenever we have if statements, it will synthesize to multiplexer. Incomplete. This is one very dangerous thing we should always avoid. Incomplete assignments, where output will remain unchanged for certain input conditions, will synthesize to what is called as transparent latches. if the process is unclocked, and if it is a clock process, it will produce flip-flops, which is a bad thing, which will be the unwanted thing. So if you are having incomplete assignment, so if you're using such a kind of code where there is an incomplete assignment, where the output is remaining unchanged for certain input conditions, it will your synthesizer will generate a transparent latch. Okay, so or in clock systems, and in clock systems you will have flip flops. Now, why is it bad? First of all, you don't want that to happen. Why? Can you tell me why this is a bad thing to happen, guys? Yes. Can you please tell me? Answer this question. Okay. First of all, we don't want any value to latch. Okay, a simple AND gate output, I need not have it latched unless and until there is a requirement. So unwanted latch is never required there. At the same time, you are consuming the hardware resource on the target device, which really is a very bad thing. As it is, we have limited resource because the target device has got limited resource. So you have limited resource at your disposal, and still you are using it for such unwanted thing. It doesn't make any sense. So you have to be very careful about these things. Now, in some circumstances, nested if statements synthesize to multiple logic levels. Okay, this also is not a very good thing and can be easily avoided using the case statement, which you are going to see afterwards. A set of else if branches can be used to impart priority to the conditions tested first. This is also one very interesting thing, why the way in which we can encode the priority also. To decode a value without giving priority to certain conditions, it go for the case statement, which we will see later on. An example is given over here. If x is less than y, then temp. So what is this temp here? Is it a signal or a variable? Tell me.
A variable.
It's a variable, correct. Okay. So temp is assigned all is all ones, else x is y and w is 0, whatever. I mean, this is just an example. Then temp is assigned some other thing. Else temp is what is this? What does this statement tell you? Last statement. What does last statement tell you? Come on. What does the last statement do? Let me put it this way. Guys, temp is assigned others.
It will be set to 0.
Yes, it simply means yes. Come again, please.
It will be set to 0.
All the bits of variable temp will be equal to 0. Okay? So we are not leaving anything hanging. We are checking for all the conditions and then doing something there. So we will redesign this D flip-flop, rather design this D flip-flop with what is called as the asynchronous reset. Yesterday I was asking about synchronous and asynchronous, and I told you the difference between synchronous and asynchronous reset. Okay, so D flip-flop is the most basic building block. Okay, because a group of flip-flops together we make what is called as a register, and this is the basic memory element to encode the states. So whenever we have the state machines, D flip-flop is always going to be there. Okay, and D flip-flop is the easiest one. You can use any flip-flop, but D flip-flop is the easiest and the most elegant one to use. Okay. So what is a D flip-flop basically? The output must copy the input at either the positive or the negative transition of the clock cycle, that is rising or the falling edge. Depending on that, we will classify it as a positive edge triggered flip-flop or a negative edge triggered flip-flop. Okay. So what we want is the value of D should be passed on to Q at the rising or the falling edge of this clock. And of course, whenever I say reset, whenever I assert this reset, in that case Q should be equal to 0. Okay, that is the requirement. Have you understood the basic requirement?
Yes, sir.
Okay. So if reset is equal to 1, then output must be equal to 0, regardless of the status of the clock. That actually makes it what is called as a asynchronous reset. So anytime this reset may be asserted and Q will be equal to 0. Alright? Whereas if you conversely, when we have synchronous reset, in that case reset will be activated. Rather, if you assert the reset pin, in that case Q will be 0 only at the edge of the clock. Whenever let reset be asserted anytime, but it will be Q will be made 0, or reset of this flip flop will be there only at the rising or the falling edge of the clock, depending on the type of the flip flop. Okay. So here we must have the output must be copy the input. Output must copy the input. That is Q is equal to D at the positive edge of the clock. So we want a positive edge triggered clock. So this is the code that you can write, VHDL code that you can write for the design of the D flip flop. Just go through this properly. See if you understand each and every part. ठीक है?
Yes, sir.
Okay, so we will try to write the code for this. Let me just open that workspace. Okay, we'll start with the new workspace itself. Let me switch over to Active HDL again. So create an empty design. Okay, what do we have? What do we require? The input, that is D, which is in type. Then you require the clock, which is in type. We require the reset, which is again the in type. Q, which is the output. Okay, so this is what I get. Are you able to see the screen?
Yes, sir.
Yes, sir.
Okay. So I will start with the uh, architecture. Process. After begin, I am supposed to have the process. Sensitivity list will compose of the reset and the clock. Okay, let us use only lowercase. Right. Then in process, I must again have begin. Okay. So if RST equal to 1, then Q is assigned 0. Then Q is assigned 0. Else if what? Yes, what should I write there? Clock tick event. I don't know why this is not giving me correct result. And clock equal to 1. Then output Q is assigned. Then E is in, right? So this should be Q. Sorry. So Q should be assigned. And if and process we already have, and so this should work. Let us see if it compiles. Let me see what has gone wrong. Oh, okay. Okay, so that is it. Now let us try to simulate it. Initialize simulation. Okay. So I will assign all this. First of all, I'll add to waveform. Remember, Q is the output, right? D, I will assign some kind of a clock again. Clock will be, okay. At a higher frequency, and reset will be a very low frequency, let us say. Oh God, what is happening here? Reset is, let us see how it really works. Okay, I can zoom into it. So you can verify whether it works as a D flip-flop here. Okay. At the same time, there will be, yeah. Okay, look at this place. When there is a reset, output is going to be 0. That is how it happens. Okay. Have you been looking at the simulation closely, guys?
Yes, sir.
Okay, so it should be very simple pattern to design and simulate the D flip-flop. Of course, we have the um, asynchronous version. Okay. All right. So let us go back to the presentation. So we saw that it is behaving exactly what we wanted it to, as far as the simulation is concerned. Functional simulation is fine. Now, what you see here is the synthesized device. So this is the synthesized device. It means it is the RTL diagram. simple plain notes. So what is happening is this will be post synthesis. Remember, you'll get this kind of figure only after post synthesis. Now in my simulation tool, I don't have a synthesis tool along with that, and that is the reason why I'm not able to. I'll not be able to show you how this is inferred, but you can very well do that after synthesis. Okay, so this is what is inferred by the synthesizer. Okay. Okay. Now, if I change the statement from clock tick event and clock equal to 0, it simply means that it becomes a negative age trigger. And in synthesis, the only change that will take place is here. So you can see that the symbol also has changed over there. If possible, I'll install Simplify Pro and then try to show you these things again. But honestly speaking, I don't use VHDL quite often, so I don't go in that much details. Okay, so this is one digit counter example. We are going to just go through this example as well. So it's a progressive one digit decimal counter. That is, it goes from 0 to 9 and back to 0. We have a single bit input clock and a 4-bit output digit. Okay, so this is the code for that. Using process, we can very easily design such a kind of a counter. Just go through the code. All right. Look at the sensitivity list. There is only one parameter there called as clock. I've declared a variable called as temp, and it is in the range 0 to 10. Now, begin. In that process, we have the begin. If clock take event, so I'm capturing the positive edge of the clock, then I'm simply incrementing this variable by 1. And as soon as it reaches 10, then I'm resetting it back to 0. That's it. Now, what is the peculiarity that you see here? Anything interesting that you see? This is quite okay, normal way of writing the code. That's all. But what is any interesting thing that you see in this code? Yes? Guys? No? We have declared a signal here. That is, actually your port itself, digit, which is out integer type. And then I have to assign it the value of temp to that digit before I get out of the process. If I try to use this digit is assigned temp after the process, it will not work. Why? Why will it not work? Guys, why will it not work?
Signal should be global.
Sequential statement.
No, because variable does not exist
Work out.
outside the process. This variable temp will not exist outside the process. Clear? Is it clear to all of you?
Yes, sir.
Okay. So this is what you get if you simulate, if you compile and simulate this piece of code. All right. So it jumps back to 0 again. 1, 2, 3, 4 goes on incrementing, jumps back to 0. Now in counter-like circuits, always use comparison statements with constant values. Okay. So if like this, okay, comparison with a constant value, we are comparing it with a constant value. Okay. This ensures that simple comparatory inference as against the full comparator inference for comparison with unknown values. Okay. So if I change the statement from temp greater than or equal to 10, simple change in statement, and you see that these are the hardware inferences. The synthesizer infers this particular hardware. So a simple change of this is also correct, but this is unnecessary. A full comparator is unnecessarily inferred and utilized. This is the extra hardware doing the same job. So these are some pointers which you should really understand how to optimize the design. Optimization is the key here. Okay. So this is when our earlier design was inferred. This is the change that you see over here. Okay. So on counter, this kind of comparator, full comparator is a costly resource. Okay. So yeah, but I think I'll stop here for today. Stretching on these things without any gap for 2 hours is not possible. Later on, we'll try to see how we can do about it. Is that fine with you?
Yes, sir.
Generally, 2 hours online like this is going to be a big boring thing. So instead of that, I want all of you to just, I've given you a couple of assignments yesterday. So start doing that. The very first assignment with VHDL that you would do is the implementation of the gates. Okay. These assignments are required for your completion also of your term work and all that. So you'll see that the very first assignment, write down the very first assignment. Write down the first assignment. Implement all the basic gates. Implement all the basic gates like AND, OR, XOR, XNOR. Okay. And simulate. Go for the functional simulation. This is the very first assignment. The second assignment is write design for a D flip-flop, asynchronous as well as synchronous, both. Are you writing this down?
Yes, sir.
Synchronous as well as asynchronous, both. That will be the second assignment. Third assignment is the encoder which I have given you yesterday. Refer to yesterday's notes. Fourth assignment is going to be a multiplexer, 16:1 multiplexer. Okay. First carry out these assignments, then we'll later on see how to go ahead with other assignments. So how many assignments in all right now I've given you?
4.
Sorry?
4. 4.
4. Okay, complete that first. Okay? Is that
Okay,
fine,
sir.
all of you?
Yes, sir.
Yes, sir.
Okay, fine. I'll end the meeting today.